Hello friends, welcome back to the Dr. Tristos channel. I'm Dr. Tristos. In our last video I left off that we were going to create a demo program and show you how to execute that using the Zilog development system. ZDS2, developed by Zilog, is for their eZ80 Acclaim series of microprocessors. I think this also works with the non-Acclaim product line, but I do not support that. So in our last episode we left off, we created a file called demo, and we're left with a blank editor screen here, and we're going to start by, I already have some code that I can paste in, and it simply has the header to begin the program. And since this is the same on most all the demo programs, it's easy for me to copy and paste this over. First is title. It's an assembler directive that tells the assembler to put at the title at the top of each page Tristos app. Next we have our define statements. Again, these are assembler directives that tells the assembler to define the startup space as in RAM, originating at 3000 hex. Next statement here is very important. Assume ADL equals 0. This is what puts us in Z80 mode or eZ80 mode. If we are in ADL equals 0, then the CPU is pretty much completely running as a Z80 chip, 16-bit addressing. That doesn't mean you can't use 24-bit instructions to access 24-bit memory. However, the first 16 bits, when you're in ADL equals 0, normally all instructions will be assumed to be in the Z80 mode. Nextly, we have the org 3000. This simply directs the assembler to originate my code that we're going to write at 3000 hex in memory. This is a standard address for Z80, for Tristos type programs that you write. We'll come down. Our first, we're going to put a label here. We're going to call this start, and let's call it start demo. And our first instruction, we'll just put a no operation, and then we'll come down and how about we load register B. Let's make it with 0, and I'm trying to think of what we can demonstrate. We're going to try to make a small loop here. So then we'll, let's go above that, load register A with a 1. And then we're going to call this label here loop demo. And what we'll do is add register A with register A. Now, the decrement and jump non-zero will decrement register B. If B is non-zero, it will then loop back to the label loop demo. So this is going to, we started B off at 0, so it decrements, it's an 8-bit register, so it's going to be 255. I can tell you now, if you start off at 0 and you do a decrement, it's going to decrement till it reaches 0. That'll be a total of 256 decrements. So this is going to loop 256 times. Let's put a little comment here. We'll call this our loop Notice that the comments are in green. This means they will not be executed. They're not lines of code that will be executed, but however are documentary comments. So now we're going to add A plus A and decrement and jump non-zero on B and loop around and do that 256 times. So let's add some other instructions in here. Let's do a no-op. We're going to load register C with register B, and we're going to, how about we load H and L with loop demo. I'll explain what these does also. So this gives us some instructions inside the loop. We have a no operation. Then we have load C from the B register. That means each time through this loop, the register C is going to get a copy of B's current contents. It's not really going to serve any purpose, except it gives us some instructions inside this loop. I'll show you why that's important later. Next we have load H and L, loop demo. Well, what does that mean? That means that we're going to load in the H and L register pair the address of loop demo. Whatever address this is in memory, I can tell you it's going to come down to approximately 3005 hex, somewhere in that range. Whatever that physical address is, we will load that in H&L. So if this physically resides in RAM memory at, for example, 3005 hex, remember we started at 3000. Here's 1 byte, 2 bytes, 3 bytes, 4 bytes, 5. Maybe this will follow about 6 probably. Anyway, that value will be loaded into H&L register pair. It's a good way to get a pointer to where something is. Again, here we're going to decrement and jump. If the register B is non-zero, we're going to take register B, subtract 1 from it, and then if it's not zero, we'll loop to our loop demo loop. So when we're all done, there's a lot of ways we could do this, but we'll say that well, we really need somewhere to go so we're just going to halt the system after it finishes this loop. No, we don't want to do that. On the development system, if you halt, oh, that's right, we're running in the simulator. So if we're running in the simulator, it won't be so bad if I do a hold instruction. If I'm running on the hardware and I do a hold instruction, it can cause you to have to do additional resets to get out of that when you're running the development system. So I try to avoid that. What happens is the CPU halts, then this program I'm using, like the ZDS, can no longer communicate with the CPU, can't examine the registers or do anything. So now we got to end this. So we're going to end, and then we're going to put the name of the program. Up here it was called Start Demo. So we're going to end Start Demo, and this is very important. This will tell the loader when we load the program that it is to begin execution at Start Demo. If I put down here loop demo, when this program loaded into RAM memory, it would automatically turn control over to loop demo if I was to call this loop demo. But we want it to begin at Start Demo label. So this is very important because I've had problems before with programs didn't run correctly, and I realized I was using the wrong label. They were starting somewhere that I didn't intend for them to start. So now if we have that, we can assemble and run this program. And it runs completely. We now have the program running. I'll expand my recording out. if we can here, to show you the okay, I had to adjust my screen there some. If we look on the right, we can see I've stopped the code from executing in the simulator. And if we look at starting at 3000 in memory, we can see our program. Here we have a no-op instruction, load A with a value of 1, load B with a 0, add. You know, we can see here our exact program in memory that we assemble on the left. If you'll notice, there's a yellow arrow at 3000 D hex, and it has a halt instruction. So we can see that this loop ran until it went through 256 times, then fell through to the halt instruction, and that's where we're sitting at now, is halt. But what else can the development system do that would be a big help to us here? Well, let's see. Let's stop this program from running. And here at the no-op instruction, I'm going to insert a breakpoint. And you'll see here, we've inserted a breakpoint, and it has a red ball on the left side from the instruction. And I'm going to I'm going to run this program again. And this time it runs, and if you'll notice on our disassembly at the right, the program counter has stopped at 3006, a no-op instruction, where we have the red ball. Now, that's handy. You know, we can stop, and then our project also allows us to view registers. And so if we look here, we can see that the accumulator has a value of 2. Part of this is cut off on the recording. I'll try to fix that on the next one, but we can see the register values here. Here's our F register, our A register, the H and L register pair. Let's go ahead and I'm going to tell the debugger to proceed. It'll step past that breakpoint that I just put in, go to the next instruction, and continue. So I did that. It's already came back around and stopped again. Let's see what we have here. We've stopped at the no-op instruction again. And it's going to keep doing this 256 times. Come through that breakpoint every time and keep stopping there. I'll start it again. And that quickly as my finger comes off of the mouse, it's already ran and stopped again at this instruction. It would do that 256 times. So this gives us an excellent way to debug the program, and it's all done inside of a simulator, and we don't have to you know, that really saves a lot in the debugging, and you know, maybe in the old days of using a Z80 chip with a monitor program, and since we didn't have protected memory and protected instructions and things, the Z80, if you made a mistake and it went off the deep end, it just went into oblivion and you had no control over it. At least here in the simulator, we can insert breakpoints, which we'll cover this more later. We would insert breakpoints and other types of software control that would allow us to more easily debug our program. That speeds execution, speeds development of programs, especially when you're doing assembly language programming. So that's all for this demo. We're going to do another demo of assembly language program, maybe a little more complicated programming and a little bit better screen setup here, trying to display all the development center at one time. But this gives you an idea of how it works, and I hope to see you back here again in future videos. Thanks.